So good morning students, this is Arvind, Assistant Professor, Department of Civil and B.Tech Kavali. So in the previous class I discussed about working principle and behavior of synchronous motor on load and on load with losses and without losses. And now in this class I am going to discuss equivalent circuit and phasor diagrams of synchronous motor. Okay, so firstly I will start with the equivalent circuit of synchronous motor. So, unlike the induction motor, the synchronous motor is connected to two electrical systems. So, unlike the induction motor, the synchronous motor is connected to two electrical systems. So, that is a DC source at the rotor terminals and an AC system at the stator terminals. So, you already know this point from the construction details of synchronous motor. Okay, so in this one, a DC source at the rotor terminals and an AC system at the stator terminal. So in this one, the stator winding, two effects are to be considered. So that is the effect of stator field on the stator winding, and second one is effect of the rotor field cutting the stator conductors at synchronous speed. Okay. So in the stator winding, two effects are to be considered. That is, first one is the effect of stator field on the stator winding and the effect of the rotor field cutting the stator conductors at synchronous speed. So this means the effect of stator field on the stator or armature conductors is accounted for by including an inductive reactance in the armature winding. Okay, the effect of stator field on the stator conductors or armature conductors is accounted for by including an inductive reactance in the armature winding. This is called synchronous reactance, that is excess. And a resistance Ra must be considered to be in series with this reactance to account for the copper losses in the stator or armature winding. Okay, a resistance Ra must be considered to be in series with this reactance to account for the copper losses in the stator or armature winding. That is shown in this diagram. Okay, this is the equivalent circuit of a synchronous motor. So in this one, I already said that for the resistance we are taking series connection of the synchronous reactance, and it consists of the back EMF. It is a stator circuit, and similar to this one we have rotor circuit. It consists of the voltage source, and we have the rotor with magnetic flux phi. Okay, so this resistance combines the synchronous reactance and gives the synchronous impedance of the machine. So the combination of resistance and reactance, it will give the synchronous impedance of the machine. And coming to the second effect, the second effect is that a voltage is generated in the stator winding by the synchronously revolving field of the rotor as shown in the figure. So the second effect is that a voltage is generated in the stator winding by synchronously revolving field of the rotor. It is shown in this connection. On the left side of this right side of this diagram we have rotor circuit. So it consists of the rotor, so it is cutted by a magnetic flux, that is phi, and we have field current IF. Okay, so that means the second effect is that a voltage is generated in the stator winding by the synchronously revolving field of the rotor. Okay, next, this generated EMF EB is known as back EMF and opposes the stator voltage, that is V. So here I am applying the KVL to this circuit. Okay, so after applying the KVL, that is the Kirchhoff's voltage law, we have the equation, that is V is equal to IARA plus J into IAXS plus EB. So from this equation we are writing RA is equal to armature resistance in ohms, XS is equal to synchronous reactance in ohms, and EB is the back EMF in volts. Okay, RA and XS is in the ohms, EB is in volts. So, and IA is the armature current in amperes and V is the stator supply voltage in volts. So, from these things we are writing the synchronous motor is said to be, so if it is in normal excitation, that means back EMF is equal to the stator supply voltage, that is V. So, if it is under excitation, that means if EB is less than V, and if it is in more excitation, that means EB is greater than V. So, these are the different conditions we have. The synchronous motor under different excitations. Okay, so that is the equivalent circuit of a synchronous motor, and coming to the phasor diagram for synchronous motor. So before going to the concept of phasor diagram, I will tell you the various rotations for each quantity at one place. So that is, here we will see in the phasor diagrams we are taking the different parameters. So those are, first one is EB, that is the excitation voltage, and V is the terminal voltage, and IA is the armature current, and phi is the angle between terminal voltage and armature current, that is V and IA, and psi is the angle between excitation voltage and armature current, that is EB and IA. The angle between EB and IA is known as psi, and delta. So delta is the angle between excitation voltage, that is EB, and terminal voltage VT, and RA is the armature per phase resistance, armature per phase resistance. And we will take, so to draw the phasor diagram, first we will take the terminal voltage as the reference phasor in order to draw the phasor diagram for synchronous motor. And phasor excitation EMF is always, the phasor excitation EMF is always behind the phasor terminal voltage, that is EB. So the phasor excitation EMF is always behind the phasor terminal voltage. So now we will draw complete phasor diagram for the synchronous motor and also derive expression for the excitation EMF in each case. So for that one we have three cases. Those are, first one is motoring operation at lagging power factor, and second one is motoring operation at unity power factor, and third one is motoring operation at leading power factor. Okay, so here firstly I will take the first case, that is motoring operation at lagging power factor, motoring operation at lagging power factor. So in order to derive the expression for the excitation EMF for the lagging operation, so we first take the component of the terminal voltage in direction of armature current IA. We first take the component of the terminal voltage VT in direction of armature current IA. So the component in the direction of armature current is, VT cos phi. So as the direction of armature is opposite to that of terminal voltage, so as the direction of armature is opposite to that of terminal voltage, therefore voltage drop will be minus IARA. This is opposite direction, so that is minus IARA. Hence the total voltage drop is, so already we have the component, that is VT cos phi minus IARA along the armature current. This is the total voltage drop along the armature current. So similarly we can calculate the voltage drop along the direction perpendicular to the armature current. Okay, so similarly we can calculate the voltage drop along the direction perpendicular to the armature current, that is the total voltage drop comes out to be VT sin phi, that is the component in the armature current, that is VT sin phi minus IAXS. This is minus IAXS is the voltage drop along with the armature current. Okay, this is for the perpendicular to the armature current. Okay, so from the triangle, so these are the diagrams. So first case, this is the first case. We have three diagrams here, three phasor diagrams. First one is for the motoring action for the lagging power factor. Okay, so in this one I am taking VT line as the reference phasor, and in this one I am taking IA. So I already said that previously the angle between terminal voltage and IA is the theta, and the angle between ET and IA is the, that is EB and IA is the psi, and the angle between VT and EB is the delta. Okay, and we have the drops, that is IARA and IAXS drops we have. So this IARA drop is always in the same direction of IA, and this IAXS drop is in the direction of VT, and we have the drop, that is IARA and IAXS. Okay, so from this one, so here we have, I am denoting with the letters, that is A, B, C, D, like that. So in this, in the first diagram, I am taking the triangle, that is BOD. So BOD, this is the one triangle we are taking. In the first phasor diagram, we can write the expression for excitation EMF is. So from this one, we are writing EF square is equal to VT cos theta minus IARA whole square plus Vt sin theta minus IAXS whole square. So these are the different voltage drop in the armature current. Okay, EF square, that is the resultant EMF, that is EF square is equal to Vt cos theta minus IRE whole square plus Vt sin theta minus IAXS whole square. Next, coming to the second one, that is motoring operation at unity power factor. So in order to derive the expression for the excitation EMF, that is EF, for the unity power factor operation, we again first take the component of the terminal voltage in the direction of armature current IA. Okay, this is the second diagram. Okay, so in this one, I am taking the same Vt, that is the reference phasor. It is common to all the three diagrams. That's why I am not showing the second and third diagram, that is Vt line. Only I am taking the differences. Okay, so in the unity power factor, but here the value of theta is 0. So in this one there is no phase difference, that means theta is 0. That means there is no means that is Vt and Ia are in the same direction. Those are in phase. That's why there is no phase difference between Vt and Ia. That's why we don't know. The angle is theta is 0. The angle theta is 0. There is no phase difference between Vt and Ia. That's why we have psi is equal to delta. So psi is the angle between excitation EMF and IA. That is the back EMF or excitation EMF and armature current IA. And delta. So delta is the angle between Vt and Et. So here we don't have those things. That's why psi is equal to phi. Okay. So in this one we have the drop, that is IAXS drop. So here I am taking from the triangle BOD in the second phase diagram, that is this one. So in this one, same triangle, that is OBD, I am taking. Okay. So from this one, we can directly write the expression for excitation EMF, that is EF square is equal to Vt minus IARA whole square plus IAXS whole square. So this is unity power factor, so there is no phase difference between any terminals, so any parameter. That's why we are writing Vt minus IAXA whole square plus IAXS whole square. Okay, that is 0. So the phase difference between the parameters is Vt and Ia is 0. Okay, and Vt and Et is 0. That's why we are not taking that thing. That's why the excitation EMF formula is EF square is equal to Vt minus IARA whole square plus IAXS whole square. This is for motoring operation at unity power factor. And coming to the third one, there is motoring operation at leading power factor. Motoring operation at leading power factor. So in order to derive the expression for the excitation EMF for the leading power factor operation, we again first take the component of the terminal voltage in direction of armature current IA. That is the same diagram we are taking. Okay. So that is the in the first phasor diagram, that is Vt Ia the same, but in this one component in the direction of armature current, that is Vt cos phi, and as the direction of armature is opposite to that of the terminal voltage, therefore voltage drop will be same to the lagging power factor, that is minus IARA. Hence the total voltage drop is Vt cos phi minus IARA along the armature current. And similarly we can calculate the voltage drop along the direction perpendicular to the armature current, along the direction perpendicular to the armature current, that is the total voltage drop comes out to be, that is Vt sin phi plus IAXS. So for the lagging power factor, that is Vt sin phi minus IAXS, but in this leading power factor the total voltage drop comes out to be Vt sin phi plus IAXS. So from the triangle, that is from the third phasor diagram, so here also I am taking the OBD, OBD triangle I am taking here also. So from this one we can write the expression for the excitation EMF, that is EF square is equal to Vt cos theta minus IARA whole square plus Vt sin theta plus IAXS whole square. So this is the excitation EMF formula for the in case of motoring operation in leading power factor. Okay, next coming to the power flow diagram in synchronous motor. So up to now we discussed about the equivalent circuit and phasor diagram of synchronous motor, and now we are moving to the next concept, that is power flow diagram in synchronous motor. So here I am showing the power flow diagram, that is the power flow diagram of a three-phase synchronous motor is shown below. So in this one, the input power of synchronous motor is electrical power and output power is mechanical power. You know already the motor definition. So the motor, the machine which is to convert the electrical input power to the mechanical output power, that is called motor. So here I am taking the three-phase synchronous motor. So in this one we have electrical input power, that is root 3 into VLIL cos phi, and mechanical power is P mechanical is equal to 3 into EB phase into IA into cos of P, phi plus or minus alpha. Okay. So in this one we have, so after giving electrical input power to the synchronous motor, it is converted into mechanical input power, in output power. So in between we have stator copper losses. Okay. So here in this one the mechanical power is developed, and this will be given to the, and this will give the mechanical and iron losses. After converting mechanical, we have mechanical and iron losses, and then it is given as output power or shaft power. Okay. So here I am considering some parameters, that is let Vt is the terminal voltage, that is for the line, because here we are taking the power flow diagram for the three phase. That's why here we are Vt is the terminal voltage per line, and IA is the armature current or line current, and EB phase is the back EMF per phase, and RA is the armature resistance per phase, and phi is the angle between V phase and IA, and psi is the angle between EB phase and IA, and input power, that is root 3 VLIL cos phi, that is equal to P in. So here input power is equal to stator copper losses plus mechanical power developed. These two combined we have input power, and in this one the stator copper loss is 3 into, for the three phase I am taking, that's why stator copper loss for the three phase synchronous motor is 3 into IA square RA, and stator input power, from this one we are writing stator input power minus mechanical power developed. So stator copper loss is equal to stator input power minus mechanical power developed. So that is mechanical power developed is equal to stator input power minus stator copper losses. So that is equal to stator input power is iron and mechanical losses plus output power. Okay, iron and mechanical losses, that is for the input power plus output power, mechanical power developed, that is equal to 3 into EB phase into IA cos of angle between EB phase and IA. So that is equal to E3 into EB phase into IA into cos of phi plus or minus psi. So from this one output power or shaft power, that is P out is equal to mechanical power developed minus iron and mechanical losses. Iron and mechanical losses, those are, from this one we are writing efficiency of synchronous motor. After taking the output power and input power, we have efficiency of synchronous motor, that is equal to output power by input power, that is equal to P out by P in. Okay. So this is the power flow diagram in synchronous motor, and next we are moving to the next concept, that is V curve and inverted V curves of synchronous motor. So here I am taking the performance characteristics of synchronous motor. Those are obtained by V curves and inverted V curves. Okay, the performance characteristics of a synchronous motor are obtained by V curves and inverted V curves. So in this one, the synchronous machines have parabolic characteristics. Okay, synchronous machines have parabolic characteristics. That is, the graph drawn is in the shape of parabola or parabolic. And next, so if the excitation is varied from low to high, that is under excitation to over excitation value, then the current IA also changes, that is becomes minimum at unity power factor, and then again increases. Only it becomes minimum at unity power factor and then again increases. Okay, but at starting lagging current becomes unity and then becomes leading in nature. Okay, at starting lagging current becomes unity and then becomes leading in nature. That means after that it will increase. And then V curves and inverted V curves of synchronous motor are used to analyze efficiency on no load and on load conditions. Okay, V curves and inverted V curves of a synchronous motor are used to analyze efficiency on no load and on load conditions. Okay, so if the armature current IA is plotted against excitation of field current for various load conditions, okay, if the armature current IA is plotted against excitation of field current for various load conditions, we obtain a set of curves known as V curves. Okay, clue to their shape similar to English letter V. That's why we are called V curves. If the armature current IA is plotted against excitation or field current for various load conditions, that means lagging, leading and unity, we obtain a set of curves known as V curves, due to their shape similar to English letter V. So I will show the diagram. It will looking like a V curve of synchronous motor, shows how armature current IA changes with excitation. Okay, the motor shows how armature current IA changes with excitation for the same input at no load, half load and full load conditions. No load, half load and full load conditions. So from V curves, it is observed that the armature current has larger values both for low and high values of excitation. That is, it is for lagging for low excitation and leading for higher excitation. Okay. So this is the V curve of synchronous motor. So here the curve is drawn between armature current and DC field current, that is IF, IA versus IF. So in this one, I am drawing the curves for full load, half load and no load conditions. So at full load we have the shape V curves, that is in this one, and next no load we have one curve, and for the leading we have one curve. So here we have unity power factor, that is indicated with the dotted lines. So the touching points of these dotted lines is for the unity power factor and remaining is for the lagging power factor and leading power factor. So the area to the left side of the dotted lines is for lagging power factor. The area right to those dotted lines, that's for the unity power factor, that is called leading power factor. And we have normal excitation for the unity power factor. And for the lagging power factor, for lagging power factor we have low excitation, and for leading power factor we have higher excitation. Okay. So for the V curves of synchronous motor, that is, if the armature current IA is plotted against excitation or field current for various load conditions. So if the armature current IA is plotted against excitation or field current for various load conditions, that is at full load, at half load, at normal load. So we obtain a set of curves known as V curves. Okay. So from V curves it is observed that the armature current has large values, but for low and high values of excitation, we have lagging and leading power factor conditions. So in between it has minimum value corresponding to the unity power factor, that is normal excitation for the V curve. Okay, in between it has the minimum value corresponding to the unity power factor, that is normal excitation. And coming to the next concept, that is inverted V curves of synchronous motor. Inverted V curves of synchronous motor. So that means if the power factor is plotted against excitation for various load conditions, we obtain a set of curves known as inverted V curves. That is a reciprocal of V. Okay, the inverted V curves of synchronous motor shows how the power factor varies with excitation. Okay, the inverted V curves of synchronous motor shows how the power factor varies with excitation. So from inverted V curves, it is observed that the power factor is lagging when the motor is underexcited and leading when the motor is overexcited. So in between the power factor is unity. So from inverted V curves, it is observed that the power factor is lagging when the motor is underexcited and leading when it is overexcited. So in between the power factor is unity. So that is this diagram. So here the characteristic diagram is drawn between power factor versus DC field current, the excitation current. So here I draw three curves. Those three curves for different curves, that is for no load, half load, at full load. So no load condition we have one curve, and for half load condition we have another curve, and at full load we have another curve. So So here the dotted lines gives the R and dotted line gives the unity power factor, and after then we are drawing one vertical dotted lines from the unity power factor we have that one. So similar to the V curve, in the inverted V curves also the dotted lines drawn in vertical. So to the right side we have leading power factor, and for the left side we have the lagging power factor. Okay, so here for the lagging power factor, the motor is under excited condition, and for the leading power factor is over excited. So in between the power factor is unity. So these are the inverted V and inverted V curves of synchronous motor. Okay. So up to now we discussed about the equivalent circuit of synchronous motor, and next we discussed about phasor diagram of synchronous motor for various power factor load conditions, that is unity power factor, leading power factor, and lagging power factor. So we draw three phasor diagrams for those three conditions and calculated the excited EMF values for those three power factors or loads, and then we discussed about the power flow diagram of a synchronous motor, that too for a three-phase. Okay, and next we discussed about the V curve and the inverted V curve for synchronous motor. Okay, so that's all for today, and in the next class I am going to discuss remaining topics in this chapter. Okay, thank you for watching this video.